So to kick things off today, I want you to just take a second and imagine the actual physical reality of the digital world that you interact with every single day.
Right, because it always feels completely weightless to us.
Exactly, yeah. When you pull out your phone or, you ask an artificial intelligence to write a piece of code or generate some high-resolution image, you don't feel any heat from that.
No, it just happens like magic.
Right. But there's this ultimate collision happening right now between that hyper-modern, weightless ambition and just ancient, unforgiving geological reality.
It is a massive collision.
It really is. So I want you to picture the blueprint for the world's largest artificial intelligence data centers, right? Sprawling across the Utah desert, consuming literally more power than entire nations, and fueled by this brand new fleet of next-generation nuclear reactors.
Which is an incredible engineering feat on its own.
Oh, absolutely. But now picture the actual ground that all of this is being built on. It is a fault line that is mathematically centuries overdue for a catastrophic mountain-moving rupture.
Yeah, we are basically looking at the textbook definition of an unstoppable force meeting a highly unstable object. The margin for error here is essentially zero.
Zero. And that is exactly why today we're taking a deep dive into what really looks like the blueprint of a catastrophe.
It's a lot to unpack.
It is. The mission today is to go through a massive stack of deeply concerning reports. We've got the internal state planning documents for Utah's initiative, which they call Operation Gigawatt. We have the structural engineering models for these next-generation nuclear reactors.
And we also have the United Nations comprehensive post-mortem data on the radioactive fallout from Fukushima.
Right, the UNSCR reports.
Hmm.
And when you stack all these sources on top of each other, this terrifying picture emerges. We're not just talking about building a few server farms here.
Not at all.
The data suggests that we might actually be engineering the perfect continent-altering disaster, like a cascading failure that could permanently contaminate the drinking water for 40 million people.
The stakes outlined in these documents are just difficult to overstate. I mean, we are examining a scenario where massive infrastructure planning intersects with literally one of the most volatile seismic zones in North America.
Yeah.
And the reports detail exactly how an overdue earthquake could trigger this sequence of events, starting with a complete grid collapse and extreme ground deformation, then moving through the structural failure of small modular reactors, or SMRs, and ending with the catastrophic collapse of an upstream dam.
It's just domino after domino. So we need to trace this whole effect from the very first falling piece. But I think before we can even understand how a disaster of this magnitude mechanically unfolds, we have to look at the sheer unprecedented scale of what is actually being built.
You have to understand the scale first, yeah.
Because the baseline numbers that are being presented to the public and then the speculative filings happening behind closed doors, they're telling two completely different stories.
Very different stories. So the context for all of this is Utah's Operation Gigawatt. Basically, it's this state-driven initiative with a really aggressive goal. They want to completely double Utah's electrical generation capacity by 2034.
Which is only a few years away.
Exactly. And the state is actively promoting this nuclear energy renaissance specifically to meet the massive incoming industrial demands from the tech sector.
Right.
But when you actually analyze the planning metrics in these sources, the disparity is glaring. So standard policy studies, like the baseline metrics from the Kempsey-Gardner Policy Institute, they show 48 operational data center projects right now, currently utilizing about 920 megawatts of power.
And 920 megawatts sounds substantial. I mean, that is almost a full gigawatt. That's roughly the output of a traditional large-scale nuclear power plant just to run the state's existing data storage.
It sounds massive until you open up the speculative long-term commercial filings.
This is where it gets crazy.
It really does. Those regulatory documents reveal a pipeline of planned capacity that entirely dwarfs the baseline. They are projecting a staggering 27,551 megawatts of demand.
27.5 gigawatts.
Huh?
I mean, put that into perspective for you guys listening. That isn't just a tech boom. That is an unfathomable reorganization of regional energy distribution.
It's the equivalent of powering several major American cities exclusively for server racks.
Yeah. And the crown jewel of this entire pipeline, like the project that really illustrates the massive physical footprint of this ambition, is something called the Stratos Project.
Also referred to in some of the filings as Wonder Valley.
Right, Wonder Valley out in Box Elder County.
Stratos is basically the ultimate hyperscale campus. The developers are slated to cover approximately 40,000 acres of private land, plus another 1,200 acres of state and military land.
It's essentially a small country.
It is, and the ultimate goal for this single isolated campus is a 7.5 gigawatt capacity. Now, to appease the surrounding communities, the developers have agreed to certain local guardrails.
Like what?
Well, they've promised a 55 decibel noise limit at the site boundary to sort of mitigate the whine of thousands of cooling systems. And they also promise strict dark sky compliance to preserve the visibility of the stars for the locals.
Which, it's fantastic PR.
Yeah.
It addresses the immediate superficial concerns of local residents who obviously don't want a glowing hunting industrial park in their backyard.
Right.
But the thing is, you cannot mandate away the laws of physics with a zoning ordinance. And this is where the math in these reports gets genuinely terrifying.
Yes, the thermal load.
Exactly. Operating a 7.5 gigawatt data center and running an associated power plant at a typical 55% thermal efficiency, that generates an inescapable total thermal load of roughly 16 gigawatts.
Because the heat has to go somewhere. The energy doesn't just disappear once the computations are finished.
Right? The servers run hot, the power generation runs hot, and it all just bleeds into the surrounding air. And I really want to make that 16 gigawatt number relatable. That is the equivalent of taking the thermal energy of 23 atomic bombs and dumping it into a single confined desert basin.
Every single day.
Every day. We are talking about a permanent, invisible pillar of heat just rising from the valley floor.
And the microclimate implications of a 16 gigawatt thermal plume in a high desert environment are profound. Researchers analyzing the Stratos project point out that this sustained heat output will literally alter the local weather patterns.
Wow.
Yeah, the models show it raising the daytime temperatures in the valley by 2 to 5 degrees Fahrenheit, and more importantly, nighttime temperatures by 8 to 12 degrees Fahrenheit.
See, I think the instinct for a lot of people is to hear a few degrees and just shrug. If it's 85 degrees instead of 80, it still just feels like a hot desert day.
Right, it doesn't sound that bad to a human.
Exactly. But these ecological reports emphasize that this isn't about human comfort at all. It's about a fragile ecosystem's survival mechanisms. High deserts rely entirely on a natural nighttime condensation cycle.
They do. The desert doesn't get its water from constant rain. It gets it from the temperature plunge at night. The air cools down, the moisture condenses out of the atmosphere, and that microscopic layer of dew is exactly how the biological soil crusts and the native flora actually survive.
So if you artificially raise the nighttime temperature by 10 degrees across a 40,000-acre footprint,
You completely suppress that condensation cycle. The ambient air never hits the dew point.
which means the valley just becomes artificially baked, the soil dries out at an accelerated rate, you eliminate those living biological soil crusts that hold the dirt together and prevent massive erosion.
You destroy the winter habitats for sensitive species like the sage grouse too.
Yeah, and most dangerously, you create the perfect bone-dry conditions for highly flammable invasive species like cheatgrass to just completely take over the landscape.
You are engineering a permanent drought localized over the facility. The sheer thermal output degrades the environmental stability of the entire region.
It's wild.
And to power this colossal 40,000 acre heat engine cleanly, without violating carbon emission targets, Utah is turning to an advanced nuclear renaissance.
So we have a valley that is artificially baked dry by a 16-gigawatt heat plume. And the irony here is that to power that heat plume without carbon, they need next-generation nuclear reactors, which require an immense amount of water and absolute geological stability.
Two things. The specific desert environment is severely lacking.
Very severely lacking. So let's talk about the nuclear side of things.
Right. So the proposed nuclear portfolio detailed in the state's filings is expansive. A primary component is the Green River Advanced Nuclear Project, which is slated to use SMR 300 reactors.
The SMRs.
Yes, small modular reactors. They're expected to generate anywhere from 600 to 1,200 megawatts. But because they are sited in an arid environment, they cannot rely on traditional river water cooling towers.
There just isn't enough water.
Exactly. Instead, they must rely heavily on massive above-ground dry cooling fans.
Okay, so that's the Green River site. What else is in the portfolio?
We also have the Brigham City Advanced Nuclear Ecosystem. The state is backing this with a $750 million workforce training hub, basically preparing the region to become the epicenter for rolling out these SMRs.
Wow, that's a massive investment.
It is. And then we also have to factor in the existing legacy assets, like the White Mesa Mill down in San Juan County. It stands as the only active conventional uranium mill in the United States, processing the regional ore necessary for this whole nuclear fuel cycle.
And the structural reports on White Mesa are highly concerning just on their own. I mean, the mill is still utilizing these aging single-layer plastic wasteliners that were installed back in the 1980s.
Yes, 1980s plastic.
And those liners sit directly over critical drinking water aquifers holding millions of tons of radioactive and toxic tailings. The brittleness of 40-year-old plastic subjected to decades of thermal cycling and chemical exposure is a massive known risk.
Oh, absolutely. But the brittle plastic at White Mesa is just a symptom of a much larger oversight. Because if we zoom out and look at the geographical map overlaying all of this infrastructure, the Stratos Data Center, the Green River SMRs, the Brigham City Deployment Zone, they share a deeply unsettling common denominator.
Right.
They are all being sited in direct contact with the Intermountain Seismic Belt, specifically the Wasatch Fault Zone.
And this is where the geology becomes the ultimate limiting factor. The Wasatch Fault Zone is a 390-kilometer-long active fault, and the reports stress that it is crucial to understand the mechanics of this specific fault, because it's a normal fault, heavily driven by the extension of the Earth's crust.
Right, it's not like the faults most people picture.
Exactly. When you look at the Wasatch Fault, we aren't just talking about tectonic plates grinding side by side, slipping past each other like the San Andreas out in California. We're talking about the valley floor literally unzipping and dropping down away from the mountains.
The mechanics are highly destructive. You have a fault plane angled deep into the Earth. One massive block of crust, which is the mountain range, is being thrust upward, while the adjacent block, the valley basin, is dropping down and sliding away.
And along the Wasatch Fault, this vertical displacement happens at a constant creeping rate of about 0.8 to 1.2 millimeters per year. Over millions of years, this dynamic is what creates those dramatic, beautiful mountain fronts that define Utah.
But the Earth doesn't move like a well-oiled machine. It doesn't just cleanly glide that millimeter every year.
No, the rock gets stuck. The friction holds the plates in place while the underlying tectonic forces just keep pushing and pushing. The stress builds up over centuries, winding tighter and tighter like a spring until the rock physically can't hold it anymore.
And then it releases 1,000 years of stored kinetic energy all at once.
And this brings us to the geological ticking clock, which is arguably the most alarming aspect of these hazard reports. Because the Wasatch Fault isn't one uniform crack, right? It is divided into the distinct segments, and seismologists have extensively mapped the rupture histories of each of those segments.
They have. And the Brigham City segment stands out as the most critical hazard by far.
Yeah, I was looking at these seismic recurrence intervals from the geological surveys, and the math feels almost absurd. The reports calculate a mean recurrence interval for the Brigham City segment, meaning the historical average time between major surface-breaking earthquakes is roughly 1,300 years.
And the elapsed time since the last major rupture on that specific segment is between 2,200 and 2,800 years.
It's not just due. It is mathematically staggering that it hasn't happened yet. We're looking at a segment that is a full millennium past its expected rupture date.
It has the longest elapsed time of any central segment on the fault, and therefore it carries the absolute highest time-dependent earthquake probability in the entire region.
And geographically, this mathematically overdue segment lies directly beneath the proposed Brigham City SMR deployment zone. Furthermore, it is situated less than 5 miles from the proposed 40,000-acre Stratos Data Center campus.
They are placing the infrastructure directly on top of the kinetic spring.
It's insane.
Yeah.
And it isn't just an isolated issue with Brigham City either. The Salt Lake City segment, which runs directly under the state's highest population density, is also fully due.
Yes, the paleoseismic data shows it last ruptured 1,200 to 1,400 years ago.
Which perfectly aligns with its own 1,300-year to 1,350-year recurrence interval. So I have to ask the obvious question. If the geological data is this universally accepted, like if seismologists know with absolute certainty that this fault is loaded with thousands of years of stress and is mathematically overdue for a major rupture, how are developers looking at this same data and deciding it's the perfect place for a 7.5 gigawatt reactor campus?
It's a great question.
Are they simply assuming modern engineering can outsmart ancient geology?
Well, the assumption embedded in these infrastructure proposals relies heavily on probabilistic seismic hazard analysis. Essentially, engineers use historical baseline data to establish safety margins for their concrete and steel.
Okay.
The problem arises when dealing with a fault that has been locked and accumulating stress for 2,800 years. The sheer volume of energy waiting to be released will be at the absolute upper limit of what the Earth's crust can physically produce in that specific region.
Right.
So to understand if any engineering can genuinely survive it, we have to look past the shaking and examine what a worst-case scenario actually does to the physical ground.
Because an earthquake of this magnitude isn't just about intense vibrations. It is about the Earth completely changing physical states. The worst-case scenario outlined in the geological hazard reports is a magnitude 7.5 earthquake striking either the Brigham City or Salt Lake City segment.
And we really need to ground that 7.5 number in reality.
Yeah, let's do that. If you lived in Utah in 2020, you remember the Magna earthquake. That was a magnitude 5.7 and caused over $600 million in regional damage, knocking bricks off buildings and cracking foundations. But the earthquake magnitude scale is logarithmic, not linear.
The math is unforgiving. A 1.0 increase in magnitude represents a 32-fold increase in energy release. So the formula reveals that a magnitude 7.5 event releases roughly 501 times more destructive energy than that 2020 magnaquake.
500 times more energy. I mean, a 5.7 shakes buildings and breaks windows. A 7.5 breaks the surface of the Earth. When this segment finally ruptures, the ground will literally tear open, creating a near-vertical scarp, just a sheer cliff of dirt, and shattered rock up to 20 feet high, instantly appearing across the landscape.
This physical tearing creates what geologists call a zone of deformation. State geological surveys mandate strict planning buffers around these known fault lines, typically requiring a 250-foot setback on the upthrown mountainside and a 500-foot setback on the downthrown valley side.
And why is that specific zone so critical?
Because any infrastructure sitting within that specific zone, regardless of how robustly it's engineered, undergoes total and immediate structural failure. You cannot design a concrete foundation, or a nuclear containment vessel for that matter, that can withstand being sheared in half and vertically displaced 20 feet in a fraction of a second.
Yeah, that makes sense.
Yeah.
But the fault line itself, that narrow zone of vertical tearing, is just the epicenter. The primary secondary damage, the devastation that spreads miles across the valley floor, is what truly guarantees this cascading disaster. And that brings us to a phenomenon that dominates these engineering reports.
Liquefaction.
Liquefaction. Can you break that down for us?
Absolutely. The legacy of ancient Lake Bonneville plays a pivotal role here. Thousands of years ago, a massive, deep inland sea covered this entire region. When the climate changed and the lake receded, it left behind hundreds of feet of deep, soft, highly saturated layers of sandy and clay sediments filling the valley basins. This flat, basin-fill terrain is exactly where the dense cities have expanded, and it is exactly where these massive data centers and nuclear sites are proposed.
Because from a developer's perspective, it's flat, it's cheap, and it's incredibly easy to grade and build on. It looks like ideal real estate.
It looks ideal, but it is a geological trap. When you subject those deep, saturated, loosely packed sandy soils to the intense, prolonged shaking of a magnitude 7.5 earthquake, something catastrophic happens at a microscopic level.
Right.
The intense vibration causes the soil particles to try and consolidate, but the spaces between them are filled with water. The poor water pressure between the grains of soil increases dramatically, and it completely pushes the sand grains apart.
So the soil literally loses its sheer strength and stiffness.
Yeah.
It stops behaving like a solid load-bearing surface and instantly starts behaving like a dense, viscous liquid.
Yes.
The ground literally turns to quicksand beneath the foundations of these megastructures.
The hazard reports break down exactly how this liquefied ground behaves, and it depends entirely on the topographical slope of the land. So if the ground is almost perfectly flat, meaning less than a 0.5% slope, which characterizes the centers of these basins, you experience a total loss of bearing capacity.
Wow. So heavy structures, like the sprawling data center server halls or the incredibly dense concrete nuclear containment modules, they simply sink into the earth. Or worse, they tilt dramatically as the soil liquefies unevenly beneath them, causing differential settlement.
Exactly. And on the flip side, Any hollow structure buried underground, like empty fuel storage tanks, massive utility vaults, or large diameter water mains, suddenly becomes buoyant in the liquid earth.
That is such a crazy visual.
They literally float to the surface, bursting right through the asphalt and concrete above them. It's like trying to hold a giant beach ball underwater.
And the devastation changes if the ground has even a slight slope.
Yeah.
Like on land with a 0.5 to 5% gradient, you encounter lateral spreading.
Yes. Lateral spreading is incredibly destructive. The deep layer of soil liquefies, but the denser, drier top crust of Earth remains somewhat intact. This massive, intact block of surface Earth essentially goes for a ride on the liquid layer beneath it, sliding sideways down the slight slope. It can sometimes move several feet in a matter of seconds.
And the mechanical shearing action of that lateral spreading acts like a giant subterranean pair of scissors. It violently snaps every single buried utility, water main, sewer pipe, and pressurized gas conduit crossing the boundary of that sliding block.
There is no flexibility engineered into regional infrastructure that can accommodate 5 feet of instantaneous horizontal displacement.
It's just impossible. And then, as you move closer to the mountain benches where the slope exceeds 5%, you face flow slides. The ground completely gives way. This results in catastrophic, high-velocity landslides and debris flows that wipe out anything in their path.
Obliterating access roads, highway overpasses, and the massive transmission towers required to move gigawatts of power.
Which brings us to the immediate, region-wide technological impact. I mean, think about a massive, high-voltage substation. It is essentially a fragile, highly calibrated forest of giant ceramic insulators and heavy transformers resting on concrete pads.
Very fragile.
When the ground underneath it turns to liquid and throws it sideways at incredible accelerations, that ceramic shatters instantly. The transformers are thrown off their mounts. The entire regional WECC power grid, the massive interconnected electrical system for the western United States, collapses in the opening seconds of the quake.
And that grid collapse triggers the first crucial failure in the nuclear systems. When those transmission corridors fall, the massive 7.5 gigawatt data centers instantly lose their connection to the generators. This causes a sudden, unprecedented electrical phenomenon known as load rejection.
Load rejection.
Yes. The massive electrical demand simply vanishes in a fraction of a second. So the operating small modular reactors, which were pushing immense amounts of power onto the grid just milliseconds prior, suddenly have absolutely nowhere to send that energy.
It's like slamming on the emergency brakes in a freight train going 200 miles an hour. The kinetic energy has to go somewhere.
Yeah.
The reactor protection systems are highly automated, so they will detect this massive anomaly instantly and trigger an automatic scram.
Right.
The systems will explosively drive control rods deep into the reactor core to absorb neutrons and halt the nuclear fission chain reaction.
But halting the active fission reaction is only the very first step of nuclear safety, because a scrammed reactor is not a cold reactor.
Exactly. And a grid collapse is exactly what triggered the cascading meltdowns at the Fukushima Daiichi plant in 2011. If we want to understand how these new SMRs are designed to avoid that fate, and why the geological reports suggest this specific Utah earthquake might completely defeat those safety systems anyway, we have to examine the Fukushima echo.
We do, because the most authoritative data we have on extreme nuclear failure comes from the UNSCR sources regarding the Fukushima accident.
UN data.
Right, UNSCR, the United Nations Scientific Committee on the Effects of Atomic Radiation. They compiled exhaustive reports detailing the exact mechanical and radiological timeline of the disaster. And the core vulnerability they identified hinges on a concept called a station blackout, or SBO.
If we look at the UN's post-mortem, the whole disaster doesn't just stem from the earthquake or the tsunami individually. It stems from the station blackout. It's not just the power lines going down, it's losing the ultimate backup at the exact same moment.
Precisely. It's the dual nature of the failure. At Fukushima, the magnitude 9.0 earthquake aggressively shook the facility, but its primary consequence was destroying the off-site AC power. The transmission lines connecting the plant to the Japanese grid were severed.
So they lose grid power.
Exactly. The reactors scrammed successfully, dropping their control rods. However, the immense inventory of nuclear fuel within the core continues to generate massive amounts of decay heat even after fission stops. It requires continuous active water cooling. When the grid dropped, the plant automatically switched to its on-site emergency diesel generators to run the massive cooling pumps.
But then, Roughly 50 minutes later, the tsunami arrived.
And the tsunami overtopped the facility's seawalls and flooded the basement levels where the emergency diesel generators were housed.
Oh, wow.
The saltwater also inundated the critical electrical switchgear required to route power to the pumps. In that moment, they lost all backup power. That constitutes a total station blackout.
With no AC power to run the pumps and the DC battery reserves quickly depleting, the cooling water just stopped circulating through the reactor cores.
Yeah.
The stagnant water began to boil off, exposing the superheated fuel rods to the air.
And the intense heat caused the zirconium cladding surrounding the fuel to react chemically with the steam, producing explosive hydrogen gas. That eventually detonated, leading to 3 catastrophic core meltdowns.
It's horrifying. So modern engineers scrutinized this UN Fukushima data and concluded we cannot rely on active pumps or miles of vulnerable wiring or diesel generators that can be flooded or physically broken.
Right. They wanted to eliminate those vulnerabilities.
And that philosophy leads directly to the design of the Holtec SMR-300 units proposed for the Utah facilities. They advertise what they call walk-away safe passive systems.
The engineering behind the SMR-300 is brilliant in theory because it attempts to remove human intervention and mechanical failure from the equation entirely.
Okay, so how does it work?
Instead of relying on electricity to pump cooling water, the SMR-300 utilizes a gravity-driven natural circulation loop. The engineers place the reactor vessel deep underground and stack the steam generator vertically above it in a tall containment column.
So it's mostly vertical.
Yes. As the water heats up in the nuclear core, thermal expansion causes it to naturally rise into the steam generator. There, it cools down, becomes denser, and falls back down to the core. It forms a continuous, self-sustaining thermal siphon that requires absolutely zero moving parts or external power.
And if that natural circulation isn't enough to bleed off the decay heat, they have an ultimate heat sink integrated into the design.
They do. Surrounding that entire subterranean steel containment vessel is an annular reservoir of water, just a massive built-in ring of coolant. If all other systems fail, the decay heat from the reactor simply radiates through the steel walls into the surrounding reservoir.
So it just slowly boils the water off into the atmosphere over an extended period, keeping the core cool for days or weeks.
Right.
Because the entire safety mechanism relies purely on the unbreakable laws of physics, gravity, and thermodynamics, it requires no AC or DC power to function.
Right. The idea is that it's immune to a station blackout.
And we naturally tend to conceptualize passive safety like a giant underground thermos. It doesn't need to be plugged into a wall. It just sits there and works flawlessly because of its inherent physical properties. But what if the thermos gets subjected to forces it was never meant to hold? What if the thermos gets crushed? This is where the brilliant engineering collides with the terrifying reality of Utah's geology.
The fatal flaw is exposed when you cross-reference the reactor's structural evaluations with the region's seismic hazard models. The standard design envelope for the SMR-300, meaning the absolute maximum earthquake force it is engineered to passively withstand without structural deformation, is a 0.5 G peak ground acceleration, or PGA.
So wait, what does that actually mean, 0.5 G?
It means the ground shaking pushes laterally with a force equal to half the force of gravity.
Okay, got it. But as we discussed earlier, the soil in the Utah valleys isn't solid bedrock that cleanly transfers those seismic waves.
Exactly the opposite. Because these facilities are sited in deep sedimentary basins, those hundreds of feet of soft, saturated Lake Bonneville soils, the seismic waves don't just pass through. The waves enter the basin, bounce off the surrounding bedrock mountains, become trapped, and severely amplify.
Oh, man.
The geophysical models predict that a magnitude 7.5 earthquake on the Brigham City segment will generate surface accelerations of 1.0 grain to 1.5 G in these specific basin locations.
So you have a magnitude 7.5 event generating a 1.5 G shockwave.
Yeah.
That is double or potentially triple the maximum force the reactor was ever designed to survive.
Yes.
So what actually happens to our subterranean thermos when it is hit with triple its design limit, suspended in soil that is instantaneously turned to violent, shifting quicksand?
The engineering reports outline several terrifying failure pathways under those extreme parameters. The most critical is control rod jamming.
Okay, walk us through that.
If the SMR is a giant subterranean cylinder, a 1.5 G seismic wave doesn't just shake it. The liquefied soil acts like a massive hydraulic press. If differential settlement causes one side of the massive underground module to sink even slightly faster than the other in the liquefied earth, the immense pressure could cause the entire steel containment module to tilt, warp, or physically deform.
And if that subterranean steel warps even a fraction of an inch, the internal geometry is completely compromised.
Yeah.
Those perfectly straight control rod guide tubes, which are literally the only mechanism stopping a runaway nuclear meltdown, could bend.
Exactly.
If the tubes warp during the violent shaking, the control rods might jam halfway down during the emergency scram. The fission reaction wouldn't shut down entirely. The core would continue generating vastly more thermal energy than the passive gravity system was ever designed to absorb.
And even if we assume the core scrams perfectly and the subterranean module holds its shape perfectly, there is an unavoidable problem above ground, the dry cooling fans.
Right, you mentioned those earlier.
To manage the immense waste heat of the power cycle in an arid desert without evaporating millions of gallons of precious river water, the plant relies on air-cooled condensers. These are massive, sprawling arrays of heavy industrial fans elevated on steel superstructures.
And under 1.5 G lateral loads, shaking violently on liquefied soil, those top-heavy steel superstructures are highly likely to buckle and collapse completely.
The structural models confirm that high probability. Even if the subterranean reactor core remains safely cooled by the passive annular reservoir, the violent destruction of the above-ground power cycle equipment means the plant is permanently disabled. It cannot be restarted to provide crucial island-mode emergency power to the devastated region.
And perhaps the most frightening aspect highlighted in the hazard reports is the total logistical isolation of the site following the quake. I mean, we detailed the flow slides and lateral spreading tearing the valley apart. The earthquake will completely destroy the local rail lines, shatter the interstate highways with massive fissures, and drop the transmission corridor.
The isolation is absolute.
The plant's literature might boast that it is walk-away safe.
Yeah.
But what happens when the reality makes it impossible to reach?
In a post-earthquake scenario where the reactor systems are compromised or physically deformed, you need immediate intervention. But emergency engineering crews, specialized heavy cranes required to move debris, or backup coolant trucks simply won't be able to physically navigate the ruined landscape to reach the site.
But the cascading failure doesn't end with a stranded, structurally deformed nuclear reactor sitting in the dark. If we trace the geographical connections here, the final, fatal blow, the event that turns this from a localized disaster into a continental catastrophe, comes from the region's hydrology.
We must map out the geography to understand the true threat here. The proposed Green River Advanced Nuclear Project sits on an elevated river terrace directly adjacent to the Green River. The Green River flows south, cutting through the canyons, and serves as the major tributary feeding into the massive Colorado River system. And sitting ominously upstream of this proposed nuclear site is a critical and highly vulnerable piece of aging infrastructure, the Flaming Gorge Dam.
The Flaming Gorge Dam is a massive concrete arch dam holding back 3.8 million acre-feet of water. It's really difficult to visualize that volume. An acre-foot is roughly 326,000 gallons. Multiply that by 3.8 million. It is an almost incomprehensible, apocalyptic volume of water suspended in a canyon directly above the valley where they want to build these reactors.
And the historical engineering data shows that this dam is already operating at the absolute razor's edge of its structural and hydrological tolerances, even on a calm day without an earthquake.
Exactly. The operational history of Flaming Gorge is plagued with near misses that prove its vulnerability to sudden stress. The reports highlight specific incidents that demonstrate the fragility of the infrastructure. Like, look at the events of June 1997.
Right, the 1997 incident.
In 1997, the operators were dealing with heavy spring runoff and had to release massive volumes of water. During the operation, a high-pressure coupling completely separated in one of the dam's primary bypass jet tubes. The resulting uncontrolled spray instantly flooded the internal power plant with 4 feet of water.
The facility's generator shut down instantly. It took terrified workers hours of wading through freezing water just to dry out the critical electrical panels enough to manually close the gates.
Wow.
And to prevent the massive reservoir from overtopping the dam while the bypass was broken, they were forced to release warm, surface-level water through the emergency spillways, which severely heat-shocked and damaged the downstream aquatic ecosystem.
And that wasn't an isolated panic either. In 2011, they faced a massive inflow emergency driven by extreme snowmelt. They had to release double the standard peak flow continuously for an entire month.
The sheer volume and velocity of the water literally reshaped the river channel downstream, scouring the banks and destroying infrastructure.
And ironically, the reports point out that severe drought is just as dangerous to the dam's structural integrity as flooding.
That's a very critical point. A concrete arch dam relies on the immense weight of the water pushing against it to transfer the load safely into the canyon walls. During recent severe regional droughts, the Bureau of Reclamation was forced to order extra downstream releases to support the Colorado River system. This dropped the Flaming Gorge Reservoir level by a staggering 35 feet.
That is a massive drop.
It is. That rapid drawdown removed the stabilizing pressure against the dam and actually buckled massive concrete boat ramps and violently broke structural steel welds on floating approaches. The dam, the canyon walls, and the associated infrastructure are highly sensitive to sudden violent changes in physical stress.
Introduce our mathematical certainty, the magnitude 7.5 earthquake on an overdue fault line. The seismic shockwaves tear through the bedrock and hit the Flaming Gorge Dam. If the concrete arch fractures under the 1.5 G acceleration, or the saturated canyon walls supporting the arch experience localized liquefaction and give way, the dam collapses.
A catastrophic flood wave, carrying the force of 3.8 million acre-feet of water and millions of tons of debris, travels down the Green River Channel.
And the arrival of that flood wave is how we perfectly recreate the devastating conditions of Fukushima.
Yes. The flood wave reaches the Green River nuclear site. Even if the developers elevated the SMR reactors on a protective river terrace, the sheer height and volume of a breached 3.8 million acre-foot reservoir would easily overtop the terrace and completely inundate the entire facility.
It violently submerges the SMR electrical switchgear, it tears away the crumpled remains of the dry cooling fans, and it permanently floods the only access roads. You now have a structurally traumatized, potentially jammed nuclear plant undergoing a total station blackout while submerged beneath rushing debris-filled floodwaters.
And the radiological threat is actually much larger than just the flooded reactors.
How so?
Because situated just 1.5 miles away from the proposed nuclear site, sitting right near the riverbanks, is the Green River disposal site.
Oh, wow. This is a terrifying existing piece of the puzzle. The disposal site is an official UMTRCA Title I facility. It currently contains 382,000 cubic yards of highly radioactive uranium mill tailings left over from the Cold War era. Right now, it is passively capped under a simple clay radon barrier.
To understand the implications of a flood hitting that disposal site, we really have to look at the historical precedent of the Moab uranium mill tailings disaster.
Right.
For those unfamiliar, a private corporation previously abandoned 16 million tons of radioactive tailings sitting directly on the banks of the Colorado River near Moab. Over the years, rain and shifting groundwater simply started slowly leaching heavy metals and radiation into the river system.
And the threat to the downstream water supply was so severe that the Department of Energy had to step in. Over the course of 2 decades, the federal government spent over $1 billion meticulously loading that radioactive dirt onto special trains to move it 30 miles away from the water.
And the Moab disaster was just a slow, passive leak caused by rain. What we are mapping out in this seismic scenario is that exact disaster, but instantaneous and exponentially worse.
If the massive flood wave scours the Green River disposal cell, it violently washes 382,000 cubic yards of radioactive tailings directly into the rushing river current in a matter of minutes. But the true, irreversible catastrophe, the event that ruins the region for generations, occurs if the SMR containment vessels, or the subterranean spent fuel pools holding the highly radioactive depleted fuel rods, are physically breached by the seismic deformation and the subsequent massive flooding.
To quantify the specific radiological fallout, we turn back to the UNSCR reports from Fukushima, which provide exact granular data on environmental contamination when nuclear fuel is compromised. The reports detail how a breached core releases a massive inventory of volatile radioactive elements into the environment.
Okay.
From an environmental health perspective, we are specifically concerned with the release of isotopes like iodine-131 and cesium-137.
Now, iodine-131 is incredibly dangerous in the short term. It has a relatively short half-life of about 8 days, but it is highly radioactive and is rapidly and aggressively absorbed by the human thyroid gland, leading to massive spikes in thyroid cancer in exposed populations.
But as the UN data shows, cesium-137 is the long-term killer.
Yeah. Let's talk about cesium-137.
Cesium-137 has a half-life of roughly 30 years, meaning it remains intensely hazardous in the environment for over a century. Crucially for our scenario, cesium-137 is highly water-soluble. It dissolves seamlessly into water, meaning it travels quickly and efficiently through groundwater systems.
And biologically, it is a chemical mimic of potassium. Because plants, animals, and the human body need potassium to survive, they actively absorb cesium-137 from contaminated soil and water, incorporating it directly into muscle tissue in the food chain.
Exactly. At Fukushima, the UNSCR data notes that massive amounts of cesium-137 leaked from the flooded basements directly into the Pacific Ocean.
But the Pacific Ocean is unfathomably large. Its sheer volume dilutes the material, mitigating the localized impact over time. But in Utah, the hydrology is a closed, directed system.
Very directed.
If the reactors breach and cesium-137 leaches into the shallow, unconsolidated alluvial groundwater beneath the flooded Green River site, it has nowhere else to go. The local hydraulic gradient flows in exactly one direction, directly into the adjacent river channel.
And that reality brings us to the ultimate devastating conclusion of this cascading failure. The Green River doesn't flow into an empty ocean. The Green River flows south and merges directly into the Colorado River.
Yeah.
If the earthquake and flood introduce a massive pulse of water-soluble cesium-137, iodine-131, and hundreds of thousands of cubic yards of uranium tailings into that channel, you permanently pollute the entire downstream Colorado River watershed.
And who relies on the Colorado River watershed for their survival? 40 million people across the western United States. That river system provides the absolute vital drinking water supply for major metropolitan areas, including Las Vegas, Los Angeles, and Phoenix.
You cannot easily or cheaply filter millions of gallons of dissolved cesium-137 out of a municipal water supply at that staggering scale.
It's impossible. And the massive agricultural systems in Southern California and Arizona, which rely entirely on Colorado River irrigation to feed the country, would be utterly compromised by radioactive uptake.
It represents a systemic failure with immediate continental implications: the destruction of the grid, the loss of the infrastructure, and the radioactive contamination of the primary water supply for the American West.
It's devastating.
But before we finish unpacking these reports, the environmental models note one final, almost surreal microclimate hazard that occurs simultaneously with the flooding.
Right, we have to look back at our 7.5 gigawatt data center, sitting in the dried-out desert basin directly over the ruptured fault line.
We established earlier that the Stratos facility generates a continuous 16 gigawatt thermal plume, creating a massive artificial column of hot air constantly rising from the valley floor. When the regional grid collapses and that massive data center instantly trips offline, you suddenly lose that immense heat source in a fraction of a second.
Wow, yeah.
Physics dictates that the massive column of hot air will instantly begin to cool. As it cools, it becomes denser and heavier. This rapid cooling will trigger intense, plunging downburst winds, essentially a massive, localized weather bomb dropping from the sky.
And these violent downburst winds will sweep aggressively across the valley floor. A valley floor which, remember, has been artificially baked dry, stripped of its biological soil crests, and ecologically degraded by years of the data center's unrelenting thermal output.
The winds scour the loose dirt and sweep directly across the vast, exposed, dry lake beds of the Great Salt Lake. The models show this generating massive apocalyptic dust storms. Because the lake bed contains high levels of naturally occurring heavy metals like arsenic, these won't just be dirt storms, they will be highly toxic dust storms. And the prevailing winds will blow these toxic clouds directly into the densely populated valleys of the Wasatch Front.
So picture the nightmare scenario for the first responders. Just as the survivors in Salt Lake City and Brigham City are attempting to dig out of the rubble of a magnitude 7.5 earthquake, with no power, severed roads, and ruptured water lines, they're blasted with zero visibility, toxic dust storms caused by the sudden death of the AI data center.
It would severely complicate, if not completely ground, any emergency response, medical evacuations, or airlifting operations for days.
It perfectly illustrates how deeply interconnected our modern hyperscaled infrastructure is with ancient geological reality, and how a critical failure in one isolated system guarantees a catastrophic failure in all the others. Let's summarize the sheer gravity of what we've unpacked here today.
It's a lot to take in.
It really is. The relentless rush to build hyperscale nuclear-powered data centers in Utah, driven by our insatiable corporate appetite for artificial intelligence, is violently colliding with the physical limits of the Earth.
Yes.
We've traced the dominoes. A fault line that is a millennium past due finally snaps, causing a devastating magnitude 7.5 earthquake. The extreme shaking triggers massive soil liquefaction, turning the ground to quicksand, which instantly buckles the regional WECC power grid.
The loss of the grid forces a station blackout at the nuclear plants.
Right. And the 1.5G seismic accelerations physically deform the reactors, defeating their walk-away passive safety designs and jamming the control rods, while simultaneously collapsing the 3.8 million acre-foot Flaming Gorge Dam upstream. The resulting catastrophic flood perfectly recreates Fukushima, breaching the compromised nuclear containment, scouring the radioactive disposal sites, and washing lethal water-soluble cesium into a river system that provides drinking water to 40 million Americans.
And as a final brutal insult, the sudden thermal collapse of the AI data center blasts the struggling survivors with heavy metal dust storms.
It forces us to fundamentally reevaluate our definition of acceptable risk. The models prove that you cannot simply zone away the laws of physics or out-engineer the absolute limits of the Earth's crust.
No, you can't.
Which leaves us with a chilling concept for you to mull over. If the marketed walk-away safety of 21st century nuclear technology relies entirely on the permanent geological stability of the very ground it sits on, are we really engineering away the risk? Or are we simply shifting the massive burden of our technological hubris onto a 1,300-year seismic clock that is already centuries past midnight? As our thirst for AI, computation, and endless data grows exponentially, we have to stop and ask ourselves, are we building the future or are we just aggressively engineering the perfect cascading disaster?